So we've got an idea of the addressing modes in detail and what they look like, but I wanted to give you a visual summary of the sort of different locations of data when you're using these different addressing modes. So we start with the implied addressing mode, which is where the opcode contains some indication of what the instruction should do, but doesn't necessarily say where that data is found. So for example, if you're incrementing, like adding 1 to a value, the number 1 isn't in the instruction anywhere. It's got to live in the machine somewhere. And so the machine just sort of has to know where to find or how to find that data. It is implied in the instruction that you're executing. Immediate, I think we're all fairly familiar. The data is in the instruction itself, and so you pull from the operand straight into the data. Then you have register and direct addressing. These are sort of the other two fairly common modes, or simple modes anyway, where register addressing, the operand specifies which register you're interested in. The register file accesses that, and there's your data. Direct addressing is the operand specifies the memory address of the data you're interested in, and then there's the data. The problem is memory addresses are, in an orthogonal instruction set architecture, memory addresses are 32 bits long and instructions are 32 bits long. So you can't fit a full address in an instruction. There are a couple ways to fix this, which we'll talk about later on, but generally direct addressing is not implemented in modern architectures. Then we have sort of the indirect versions of addressing. This is where you're accessing memory, but the address isn't in the instruction. It's somewhere else, right? So in register indirect addressing, the operand tells you where in the register file to find the address, and then that value is used to access memory. Fairly straightforward. And then memory indirect, the operand gives you a memory address, and that memory address specifies the address of the data that you're interested in. Again, because this is an address in the instruction, this is a little bit unusual, but the concept of having a set of addresses of data in memory, this is used all the time, right? A vector table is like this. You go to the interrupt vector table, that has the address of the data you're interested in, then you go to that data. So the concept is useful and is used regularly, but as an addressing mode in an instruction, it's a little unusual. And then you have these three more complicated addressing modes where you calculate the address in memory you're interested in by adding some numbers together. In base plus offset addressing, you're adding the register address. So the operand contains a register address and an immediate value. The register address contains the register contains an address. That address is offset by the immediate value and used to access memory. This is the same thing that happens with base plus offset addressing. They're basically the same thing. PC relative addressing and base plus offset addressing. The only difference is that the base register is the program counter in cases where you're doing something like branching. So if you branch to a target, you're going to make the program counter equal to some offset from the existing program counter. And the program counter there is an implied address, because you never say program counter within a branch. You just say branch to this value, and the machine knows that it's got to take the PC, add or subtract some value, and then that's the new PC. Then you have indexed or scaled addressing. This is where you have the operands specify two registers, and then the register file looks up both of those registers, adds them together, and then uses that as the address in memory. This is very common in a lot of modern assembly languages. The scaled version, we'll see there are some instruction set architectures that allow you to actually scale one of the offsets before you add it together. And then auto-indexed is another sort of special case of this base plus offset, where you're taking the register file contains the base register that has the memory address. Then you're going to add some offset to it, just like in base plus offset addressing. But in this case, you're using it not just as the address of memory, but also as the new value for that base register. So you can access data and also point to the next data in a single instruction. Those are sort of the general addressing modes that we see. And here are some examples of modern instruction set architectures that implement these addressing modes. So everybody does immediate, register direct, register indirect, base plus offset, PC relative. These are very common and sort of the fundamental instruction set or fundamental addressing modes for ISAs today. But here are some examples of other addressing modes you might not have seen. Direct addressing, like we talked about, is implemented in x86 because x86 has variable instruction lengths. You can say, do a thing, and here's the complete address of the thing I want you to do, right? You can't do that in orthogonal instruction set architectures because, again, the memory size, the address size, is the same as the instruction size. MIPS has like a pseudo version of direct. They call it pseudo direct addressing, where you take the sort of the most of the size of the instruction, and then you sort of put together a memory address. You do this by assuming, first of all, that memory addresses for instructions are word aligned. And that's a good assumption because if an instruction starts at memory that ends in 00, the next one is going to be 01, 10, 11, 00 again, right? Because 32-bit data instructions are 4 bits long, and so if the last 2 bits are always going to be the same, right? If it starts at 00, the next one's also going to start at 00, and so you don't need to encode that. So there's 2 extra bits for free, and then the last 4 bits. So this is assuming that you have 6-bit instruction opcode, which is what MIPS does. So you have a 26-bit pseudo-direct address. You tack 2 zeros on, that gets you to 28 bits. And then the last 4 bits to get you a 32-bit address are just taken from the program counter. So this is almost direct addressing. They call it pseudo-direct addressing. You have most of an address in the instruction. Then you have indexed addressing, where you take 2 registers and add them together. x86 does this. ARM does this. You have scaled addressing. Both are also available in x86 and ARM. In ARM, it's really interesting because one of the operands can always be shifted. There's a barrel shifter built into the architecture so that whenever you are adding 2 numbers together, one of those numbers can be shifted by some amount. And so if you shift that number by 2, you're multiplying it by 4, and that lets you get to the next word in your data structure instead of just the next address in your data structure. So these are scaled addressing. Auto-indexed is also in ARM. ARM has some really interesting and powerful addressing modes. That little exclamation mark there says it's auto-indexing. What that does is the address of this data is at R1 plus 4, and then the exclamation mark says, and put R1 plus 4 back into R1, right? Keep that value and put it into R1 so that we're already pointing at the next value when we're done with this instruction. Puts a bunch of stuff together in one place. And then memory indirect, again, is very uncommon, but LC3 implements memory indirect if you want to look at it. It points to an address, and then that address points to an address. This is a common structure in assembly languages. We do this all the time with vector tables and stuff. But to have it actually implemented as an addressing mode in an instruction is somewhat rare.